Right.
Hello everyone, welcome to this short video by BCS London Central Branch. Today we are joining Colin Bradley to talk to us about blockchain in a post-quantum computing world. So Colin, if you just want to introduce yourself and tell us what is this all about?
Sure. Thanks very much, Amber. Quantum computers and blockchain are great passions of mine. I first got introduced to quantum computers probably back in the 90s when I was in university, and I followed the progress of quantum computers up to present day. And today we have the likes of Google releasing a 56-bit or qubit quantum computer, and also IBM creating a platform for people to go and program on a quantum computer if they want. It's available in the cloud. Blockchain, I'm a relatively latecomer to blockchain. It's only in the past 3 or 4 years that I started exploring blockchain and what the effects are to society of blockchain, and understanding that blockchain isn't just about Bitcoin, it's much more than that. And I began thinking, well, if quantum computers are really, really good at solving complicated problems, then what are the effects of a quantum computer going to be on the blockchain?
Okay, interesting. So let's take it right back to the beginning so everyone can follow what it is you're talking about. So can you explain to me in very simple words, what is blockchain?
Oh, wow, okay. So in very simple words, what is blockchain? So like the name describes, it is a series of blocks, and each of these blocks contain a piece of data. Now, what makes blockchain unique is the fact that the data of each subsequent block is created from a hash of the data in the previous block. So a little bit like a string of pearls, that if you remove the middle pearl, it would be quite noticeable, and it's a tough and difficult thing to do. So people view blockchain as a source of data, as a source of truth, which is immutable, which means unchangeable. The great beauty about blockchain, and one of the reasons why it was first created, it was actually devised by a chap called Satoshi Nakamoto, and nobody knows if it's a man, if it's a woman, or if it's a group of people, back in 2008. And if you think about what was happening in 2008 with the banking crisis, Satoshi wrote this white paper, and he devised this distributed currency called Bitcoin, which was based on blockchain technology. And the key thing about blockchain as well is that it's distributed, so everyone has a copy of the ledger. So rather than something being centralized with your bank or with an organization, everybody has a copy of this ledger local to them or in the cloud.
Okay, interesting. And how would you describe it to a 5-year-old, for instance?
I was afraid you'd ask me that question. So how you would describe this to a 5-year-old? I've been having a bit of a think about this, and I was helped out by a good friend of mine, and they advised me is like the best way to describe this is using Lego. So if you can think of a Lego block, and maybe you have a group of children and they all write something on a Lego block, and they join these blocks together. That's pretty much what we're doing with blockchain. But everyone has a copy of that tower that they're building, and you can't remove a middle bit of the tower without somebody noticing that that particular tower has come out of sync with everybody else's tower.
Okay, that makes sense to me. Great. And why do we actually need blockchain?
So there's lots of reasons why we need blockchain or a technology like blockchain. And blockchain is just one version of a group of technologies called distributed ledgers. How I like to explain distributed ledgers to people and blockchain to people is that, well, if you consider a distributed ledger to be a vacuum cleaner and a blockchain to be a Hoover, then all Hoovers are vacuum cleaners, but not all vacuum cleaners are Hoovers. A Dyson or Philips or something different like that. So it's just a group of technologies, and they all work in slightly different ways. But the central premise with all these things is that the immutability, so you can't change stuff that's in there, and it's distributed, so everyone has a copy. Now, why we need these technologies is like, I'll give you a great example I spoke about just recently to an organization. The World Wildlife Fund are trying to use a blockchain to stop illegal fishing in the South Pacific Sea, where there's a big problem with the overfishing and illegal fishing of bluefin tuna. And bluefin tuna, excuse me, has declined to about 3% of its original biomass from when it was first recorded. But illegal fishing also brings in stuff like slavery, forced labor, poor working and dangerous conditions for the fishermen and for the people who go and do that. And they're using blockchain to actually tag the fish once it's caught and track it all the way through the supply chain. It's all stored on the blockchain. So it will get to a point where you go to your Waitrose or to your Sainsbury's or your Tesco's or your Aldi, and you can actually scan the package of tuna to see when it was caught, who caught it, how it was caught. You know, you see these things being pole caught or line caught. And what they're trying to do is reduce the amount of illegal bluefin tuna which is entering the market. And that's just one example. Yeah.
Cool. I love hearing about all the different use cases for blockchain and distributed ledger. I think more often in the press, it's spoken only in the terms of cryptocurrency. So great to hear some other examples.
Absolutely, and crypto, and it probably, if you look at cryptocurrencies, it's been the tip of the iceberg of what blockchain can actually do. There's so much more uses and benefits to us as a society that blockchain will bring.
Nice. Okay, so moving on to the second half of this chat.
Yeah.
What is a quantum computer?
Wow. Okay. So what is a quantum computer? And I'm guessing you want me to describe this as simply as possible.
Okay. Yeah, imagine I'm a 5-year-old.
The 5-year-old again. Okay, cool. So a quantum computer works a little bit differently to a normal computer. So if we consider that a normal computer, if we want to represent anything in a normal computer, it has to be in the form of 1 or 0. So, you know, in simple terms, the current is there, the current is not there, the light is on, the light is off. And it does things in a very serial manner. So it has to, so if we had 4 cards, for example, and one of those cards was a queen and the other 4 were aces, in order for us to determine which one, and we held the cards face down, and we gave the computer a problem to solve. In order for it to determine which one was a queen, it would have to do about 2.3 processes, 2.5 processes within the computer to be sure that it can actually find the queen. With a quantum computer works with something called qubits or a quantum bit. And this was first devised, I think the term itself was actually devised in the mid-1990s. And the person's name escapes me. I think it might have been David Deutsch or Di Vincenzo, who came up with this term, the quantum bit. And what the quantum bit is that it can be a 0, it can be a 1, or it can be both at the same time, which is a little bit difficult to kind of get your head around. But if you consider, and I don't have a penny on me, okay, let's use my tiger. I wasn't going to use this tiger, but I'm going to use him anyway. So you can see here, we've got a tiger, and you can see his face, and you can see his back. Okay, with a quantum bit, it's almost like the tiger is spinning. So it's both, if this was spinning really fast, and I said, Amber, is it front or back of the tiger? You would say, well, you wouldn't know, okay, until we stopped the tiger and made a measurement. So quantum bits like that, until it's actually observed, it exists in both states at the same time.
Okay.
So to use the card example as well. So we've got the 3 aces and the queen, and we turn them face down, and we ask the computer to find out. A quantum computer, a 2-bit quantum computer, can do 2 to the n operations, which is 2 to the number of qubits. So 2 to the n. So that would be 4. hopefully, if my maths is good. 2 to the n is 4 operations at once. So it would only need to do one operation to find that, to find the queen. And when you consider that Google just released a 56 qubit computer, that's 2 to the 56 operations it can perform in one execution. So massive and massive and massive amount of computational power.
Okay. And you keep mentioning qubit. What
Yeah.
exactly is a qubit?
Wow. Okay. So what is a qubit? That is a really good question, because a qubit. Okay, let me go back a little bit. So a qubit, there's lots of different ways of realizing what a qubit is. In the same way, in the same way that there's lots of different ways to make furniture. I'm just looking for ways in which to explain this. So there's lots of different ways in which you can realize what a qubit is. You can use different isotopes. You can use different ions. You can use beryllium ions. You can use calcium ions. You can dope silicon with arsenic or phosphorus. You can, there's about, I'd say at least 10, 15, 20 different ways in which to realize what a qubit is, okay? Some ways work better than others. There was a big breakthrough a few years back where they actually realized a qubit in silicon, and the University of New South Wales in Australia, I think, probably not 100% on this, but they made a massive advancement in the fidelity of a qubit doped within silicon. And fidelity essentially means how closely the performance of the experiments matches the experimental, the sort of theory behind it. This is a massive advancement because before this, qubits were housed in cathode tubes and big cryogenic stuff, and they still are to a certain degree. But the fact that we've realized a qubit in silicon means that we can start to make things smaller. And this is what we see with the IBM computer and the Google computers. These are qubits which are etched in silicon.
Wow, fascinating. And
I hope so.
No, you definitely know a lot about this topic. So, okay, you mentioned already like the IBM quantum computer, and that Google's playing in this space as well. Can I go out and buy a quantum computer today?
Not unless you have lots and lots of money. There are actually quantum computers that you can buy today. There's a Canadian company, and I'm pretty sure they're Canadian, called D-Wave, and they produce a type of quantum computer which isn't based on quantum logic gates. So the computers I've been talking about so far, and the qubits I've been talking about so far, are based on something which is called a quantum logic gate, or a universal quantum logic gate. The D-Wave computer uses a different type of quantum technology called quantum annealing. I don't know a great deal about it, but I do know that there's some discussion. There was an MIT paper released, and there was a Caltech paper released as well, which said actually the type of speed up that they're getting using the D-Wave computer, you would see a comparable, you could get comparable results with a traditional type computer that we have. The thing about the IBM type computer and the Google computer is that you can't really go out and buy one. These are big machines. They cool the chips down to about 2 millikelvin, and if you know your Kelvin scale, everyone's familiar with Celsius. So 0 on the Kelvin scale is roughly minus 273 point, I don't know, 1 something degrees Celsius. So they cool these things down using, you might have seen them actually. They look like part of the TARDIS has been taken out and jammed someplace, but it's think it's called a dilation chamber, which is a fancy name for like, yeah, it's a fridge. It just cools things down and down and down and down. And one of the reasons they do that, I'm completely off topic here with, can you actually go and buy a thing? The answer is no, you can't go and buy it. But one of the reasons they have to cool these chips down is to reduce the amount of energy and heat that's in there, because with anything to do with a qubit, you want to take that jiggling out of it. So you want to reduce the amount of energy as much as possible, so that you can hold the gate state or the qubit state for as long as possible. Is probably the easiest way of saying it. No, you can't buy it. No.
Okay.
Maybe on Amazon. I don't know. You can get everything on Amazon.
I'll take a look later on and see what I can get. All right, taking it out of the super technical area we just went into there.
Yeah.
I've seen quite a lot in the news and in different articles that I've read, the term quantum supremacy coming up quite a lot. Can you give me a quick overview of what do you mean by quantum supremacy?
So quantum supremacy, now Google have actually announced that they've achieved quantum supremacy. so that's a quantum computer that can basically solve any problem that's been thrown its way. Now, typically, quantum computers today are used to solve and to model quantum problems, right? So they're not actually solving any real world problems. One of the difficulties, so for example, a real world problem would be profiling the weather. So what would the weather look like over the next 5, 10, 15, 20, 30 days? What would the weather like? Quantum computers would be really good at that. The traveling salesman problem, which you've probably come across. Again, quantum computers would be really good with that. Anything which involves like an exponential type problems, so for developing new antibiotics or anything like that, quantum computers would be really good for that. Quantum supremacy means that someone has actually generated a quantum computer which is stable enough and they can hold a qubit in a state which long enough to start asking these questions and solving these problems. Has someone achieved quantum computer supremacy? We might never know whether someone has achieved it. For example, if you look at Enigma in World War II, the Enigma was the code, the cipher was broken at Bletchley Park here in the UK. But the Allies, or the Allied forces, were very careful to only use it. They couldn't directly use it. So if a ship was going to get bombed, they couldn't steer the ship out of the way without giving the game away that they'd cracked the German code. Similarly, if someone has a quantum computer now which can break RSA encryption, for example, would they publicize it? Probably not, because the minute they start publicizing it, it's a case of, okay, whether it's China, whether it's the US, whether it's Ireland, you know, if they've got a quantum computer, would they actually publicize it? Because actually they've got the secrets of the world at their fingertips. The minute they start publicizing it, people start protecting their systems against it.
Mm-hmm. And so looking at that in comparison with blockchain, you said at the beginning that blockchain is
Sure.
often around solving really long, big, potentially exponential problems. And that's exactly what quantum computers are great at doing. So what would be the effect of quantum computing on the use of a technology such as blockchain?
So quantum computing uses algorithm, or sorry, excuse me. So blockchain uses algorithms to both hash the data, but also for key encryption systems. So where a quantum computer will come in, there's two algorithms in particular, the Grover algorithm, which gives you an exponential speed up in solving hashing functions, is probably the easiest way of putting it. And the Shor algorithm, I think Peter Shor was an IBM engineer, scientist, or fellow in the 1990s, and he developed this algorithm called the Shor algorithm, which gives you the ability to factorize large integers. When you consider that RSA encryption is based around taking two prime numbers multiplying them together, which is easy to do, and coming up with an even bigger number. Suddenly, if you have a quantum computer, you can take that big number and start finding out what those prime factors are. And once you do that, you start breaking the code. So it becomes so the blockchain then becomes then you put a question of the blockchain saying, well, is this actually immutable? If someone has the ability to either duplicate a signature or break the key encryption or replace hash data with something else in the middle of a blockchain, then you start putting a question over whether or not the blockchain is truly an immutable source and a source of truth.
Okay. And you said before with quantum supremacy that we wouldn't necessarily know if someone had achieved quantum supremacy.
Yeah.
So how do we know whether a blockchain has already been hacked?
Well, I don't know. If we look at most experts in the field, and I don't consider myself an expert. We've got people who dedicate their lives to this to this research. Most of the experts in the field believe that we won't see a computer of that power capable of breaking those codes and making the manipulations that I just spoke about for at least another 10, if not 15 years. Some people put it much further than that. If you look at, however, steps are being made both on the blockchain front and with the NIST, the NIST in the US, and I want to say NISA in Europe, NISA in Europe, to start looking at they understand the threat of quantum computers to people's secrets, and they understand that things need to be done to protect people. An interesting thing by a line from ENISA was a paper that they released about 2 years ago, and I'm just going to read a little bit out of here. It says, quantum computing is still perceived as both an opportunity and a threat. Mastering quantum computing might allow solving classes of problems that cannot be solved with classical computing in a reasonable time. The public key encryption cryptography solutions resistant to quantum computers has been emerging, although the wider problem of migration has no viable solution in sight. So what that says is that developing solutions which are quantum computer proof, we'll say, or resilient to quantum computer, that is underway. How do you then take everything that's been encrypted using an old form of an encryption and migrate that to new encryption, which is resistant to quantum computers? That is a problem. That will continue to be a problem until someone does some work on it.
Okay. And just sort of starting to wrap things up a little bit.
Sure.
When we talk about someone wanting to possibly use a quantum computer to hack a blockchain, are we talking about a teenager in their bedroom or criminal gangs in this case?
That's an awesome question. So growing up in the 80s, as I did, there was always the spotty teenager in their bedroom hacking into the government. They always called it the mainframe when it clearly wasn't a mainframe. It was something different. But there was always that perception of the individual hacker. With a quantum computer, given the speciality, and we're only at the very beginning of quantum computers, like building the language for quantum computers. So if you look back at assembler language, we're only building the language. What we're looking at nation states who have the resources, the manpower, and the will and desire to actually develop this and target their hacks, we'll say, at a specific target. The value in hacking a blockchain, for example, to mess up the tuna stocks coming, or the validity of the tuna stocks coming from the South Pacific, probably not high on the radar. if but it might be something else. Some governments, like Israel, for example, have actually started to using something like quantum communications, which is a whole discussion on itself on how you use quantum technology to secure communications between two people, without an eavesdropper. An eavesdropper can come in between, but both people would know that there is an eavesdropper in between. So we already see steps by banks, by nation states, to start protecting themselves from the quantum computer supremacy. But also using quantum computers and funding quantum computers. There's billions and billions and billions of dollars going into research in this technology area, globally. It's so important.
Yeah. So it kind of sounds like what you're saying is that blockchain is definitely going to be impacted by the likes of quantum computing, but equally quantum computing itself can be used to improve and enhance
Absolutely.
the blockchain. So it's a little bit of the two in a race together to continually improve.
Absolutely. Yeah, you can use quantum key encryption, but the problem will remain until someone solves it. I'm not personally going to solve it, but how do you then migrate, let's say, blockchains or distributed ledgers to use a stronger form of encryption? And it may seem like a little while away, but if we had a message from the future, from an alien race, and they said, hey, in 10 years time, we're going to turn up, you guys are going to be in trouble, what do you think we would do? We'd start preparing. And I think that's what people need to do now, is start thinking about it, start preparing, and start planning.
Amazing. Well, I'm sure we've only scratched the surface with what is such a truly fascinating topic. And it's something that I really do think it's going to have a direct impact on all of our lives in sort of the coming years. So thank you for giving us a brief insight to all of that. So yeah, thank you very much for coming to us today. And yeah, hopefully we'll hear more from you in the future.
Okay, it's been great talking to you again. Take care now.
Thanks a lot. Bye.